So welcome back to the parallel session, multi-messenger astrophysics and supermassive black holes. So the next speaker is Kelly Holly-Bockelman from Vanderbilt University, talking about the handy massive black hole modular timescale, scaling relations for subgrid models. So Kelly, are you here?
All right, folks.
All right.
Thank you. Today, I want to talk to you about some work that we're doing to try and make a little bit of a relation or an equation or a handy, a handy relation for folks who want to figure out what black hole merger timescales are, because it's pretty different in the LISA regime. And let me just take a step back and explain. The picture here is if you ask an astronomer what a massive black hole is, they'll probably think of something like this. This is Centaurus A. It's a giant elliptical galaxy. The black hole jets sort of suffuse the entire galaxy. As you can see in radio, this black hole is 1 billion solar masses. And that's not the kind of thing that a LISA astronomer will think of. So let me just pause and let y'all revel in the fact that LISA black holes are quite different. As Jesse sort of mentioned in the plenary talk on the first day, LISA black holes live in an entirely different type of galaxy and in totally different systems. So here are some Milky Way mass black holes, 10 to the 6 solar mass black holes. They live in spiral galaxies that don't have bulges in them at all, and they're revealed in X-rays. They can live in low surface brightness galaxies like Malin 1. Here's another Milky Way mass black hole as well. They live in dwarf galaxies. This is a very famous one by Amy Rines, Hanai's 210. It lives in something that's kind of like the mass of the Large Magellanic Cloud. Here is another recent finding in a little satellite galaxy called Leo 1. There's 1 million solar mass black hole. And at the center of the Milky Way, there's 1 million solar mass black holes. So you can see the huge dynamic range of places in which LISA black holes live. Here are some other dwarf galaxy findings, again, sort of 1 million solar mass black holes, and they tend to live off center of their host galaxy. So these were called wandering black holes in dwarf galaxies. There's some other even lower mass black holes found sort of in the outskirts of galaxies. There's one of the early ones, HLX1. Here's a very recent one. This is Andromeda. It's got a 10 million solar mass black hole. It has a little satellite galaxy that has an intermediate mass black hole in it. And same thing for this galaxy. This little tiny satellite shown brightly in X-rays because of a tidal disruption event. Oops. That tidal disruption event, here's an artist's rendition of it. And it allowed us to sort of estimate what the mass of that black hole is. And it's even lower mass, again, sort of in the Milky Way regime. Of the sort of large galaxies, one characteristic is that many of the black holes that are found in LISA that sit at the centers of galaxies live in the type of galaxies that have nuclear star clusters. So this is an example of a nice spiral galaxy that at the center has a nuclear star cluster. Here's another. This is a great review should you want to learn about nuclear star clusters. The big deal is that if you look at the stellar mass of a galaxy and the fraction of those galaxies with nuclear star clusters, they're pretty huge. Roughly 80% of the galaxies that are kind of in the stellar mass range to host LISA black holes host nuclear star clusters. And those have very different properties. So nuclear star clusters, you can think of them as like a super globular cluster. They are the most dense stellar objects in the universe. And so this is an example of that. Sorry, it's in surface brightness, which is kind of like a proxy for stellar surface density as a function of radius. And you can sort of see if this particular galaxy just had a flat kind of density profile, stellar surface density profile, that's what it would be. But again, sort of rise 4 orders of magnitude in stellar surface density. So super dense, but also they're flattened and rotating. So what this plot shows you is the fraction of the kinematics that goes into rotation versus velocity dispersion. And so this would be highly rotating, and this is not. These are all galaxies with nuclear star clusters, and here's the ellipticity, or sort of the flattening, the 2-dimensional flattening of that system. So they're flattened and rotating, either co or counter, depending upon what it is interacting with. Okay, so let's put that in the context of merger timescales for black holes. So as you all know, the black holes may exist in 2 different galaxies. As the galaxies merge, the black holes come together first through dynamical friction and then through 3-body scattering. And that's the part that my team and I work on and have for years. So when the black holes become bound, the only way that they can get closer together is by basically bleeding energy and angular momentum from the orbit, either through gas or through stars. And we concentrate on stellar interactions. So the black holes can do a few body scattering, sort of kick a star out or give a star more energy, and then the orbit becomes closer. And that used to, folks used to think that this took forever. It's because of this thing called a loss cone. So just really quick, this is angular momentum. And so essentially circular orbits are up here, radial orbits are up here, because it's sort of a ratio of angular momentum to the angular momentum that you would have at the same energy for a circular orbit. This is energy, but black hole is this way. And so you see a whole bunch of stars here, and you see this little empty space. And that is because in this region, all the stars that could interact with the black hole have been kicked out. This radius right here is sort of the hardening radius, that radius where black holes can become closer if they kick stars out. And you can see anything sort of in this region in energy angular momentum space has mostly been kicked out. These stars can have been kicked, but they can come back. So you can see the loss cone is evacuated really quickly in this model here, which was of a static spherical model. And that's the problem. Because as you'll see, once you relax those really stringent criteria of a perfectly spherical system that's static, etc., then that loss cone can get refilled, but we had to show it. And this requires a very computationally expensive approach. And I can talk to you about how taking shortcuts can lead you to a misleading answer. So I could talk a lot about that, but maybe I won't, because I just want to tell you what we got. Nonetheless, what we did was we built a model of the galaxies that were less perfectly symmetric. In this case, like our very first case, we just built something that was static, but axisymmetric. It was not rotating, and then we basically allowed the black holes to sink closer and closer together due to few body interactions. But the interactions were calculated directly without kind of shortcuts with smoothing or fixed potentials or statistical techniques to figure out the scattering rate. So anyway, details about that there. And what we found, and what lots of people found later and even earlier, was that as soon as you relax this concept of symmetry, so allow the galaxies to be axisymmetric or triaxial or rotate, then entirely different orbit families are allowed in those potentials. And so here's an example of orbits that we found in a nice non-rotating axisymmetric galaxy. They're called saucers. We also found pyramids and a bunch of other cool orbits, but the big deal is that they're centrophilic, A, and that means they go towards the center, quite easily, and so they can fill the lost cone pretty well. But also in many cases, especially in triaxial systems, the orbits don't have to conserve angular momentum at all. So they kind of sweep through that lost cone and they can refill it really quickly. In fact, so quickly that we consider the lost cone always full in this case. So in the case that we showed, 60% of the stars were this type of orbit that can interact with the black holes really efficiently. So just let you know, this thing that you may call the final parsec problem really isn't a problem. What it means is that you've made a system, or you've assumed that that your black holes are orbiting in a system that is spherical and static and so forth. Okay, so yeah, so if we had roughly 2 × 10⁶ solar mass binaries, then we calculated that it would take roughly 300 million years to merge in this very equilibrium type galaxy, but just flattened. And then we, over the years, started making things more complicated by adding rotation and by doing triaxial systems. And let me just walk you through this plot just really quickly. This is the inverse of the separation between the black holes. Sorry, I know it's weird, but this is really close together. This is far apart. Around about here is the separation in model units that it would take to pass from 3-body scattering phase to the gravitational wave merger regime. And you can see in a spherical system, you never reach that case. You do barely reach it if you're just axisymmetric. And if you're rotating, then the orbits shrink even faster. And just a word about why it's so computationally expensive. This marks the evolution of the black holes when you have a differing particle number. And interestingly enough, you can see when you have very few particles, it looks like the system shrinks faster, right? And as you add more and more particles, then the system well, it looks like it takes longer to merge, but that is all because of numerics. Because you can also refill this lost cone just through noise, just through this thing called artificial 2-body scattering that comes from a simulation that has a lot of numerical noise. And so once you add particles, you sort of go better into the collisionless regime and you can resolve the physics. Anyway, that's part of the reason why these are so expensive, because you need a couple million particles to accurately resolve the physics. Anyway, some cool stuff.
Kelly, you have 3 minutes left. Sorry,
how many
minutes left?
Perfect.
3.
I will not tell you the cool things. So what we did is, with a whole suite of simulations in which we built the galaxy models to match observations from things like the Sirsic profile and rotation, etc. We calculated coalescence times and so forth and tried to find relations. And one easy relation that folks already knew was that the shrinking rate of the binary is related to the stellar density, and that's nice here. The dots correspond to whether or not the system, the black hole came in co-rotating or counter-rotating, or the gray, the system was not rotating. But that coalescence time isn't as correlated with stellar density as we thought. So it's much more complicated. So if you have systems that come in co-rotating, their coalescence time in log of gigayears is much longer than if the system is counter-rotating and the eccentricity is high at the end. So you can see a lot of scatter here, but you also sort of see 2 paths. And the big deal is that this scatter means that we've got some higher manifold going on, and that these are projections of that higher manifold. So we see the coalescence time, log of the coalescence time, as a function of binary black hole mass. And again, you sort of see 2 categories, but a lot of scatter. One clue comes into the final eccentricity. So the final eccentricity of the system really matters in determining the coalescence time, even if something has a high scattering rate. If it comes in at a low eccentricity, then it takes much longer to merge. That we sort of knew, but it's nice to see it plotted here. And finally, this is our handy relation. I'm holding you in suspense because this is not published yet, but let me show you. So this is given the principal component analysis regression. We have, I think, 5 principal components here. And with that prediction, that is the yellow, versus a sort of one-to-one relation, we are able to predict the black hole coalescence time as a function of things that astronomers observe. Things like V over sigma, the rotation, the Sirsic index, which maps to density profile, remember, the black hole mass, the eccentricity, as we showed you, was a big component, and the galaxy size. So stay tuned, but I think this will be really useful to use for folks who are doing simulations, for example, and they want to model black hole merger rates as a global thing, but they don't know how much time to assign for a black hole merger timescale. This will definitely help. So you can go look at a galaxy and predict how at least for realistic galaxy shapes and sizes and black hole masses, how long they take to merge. Okay, there, done. Thank you.
All right, thank you so much, Kelly, for the interesting talk. So I think the floor is open for the questions. Oh yes, Roberto, you were the first to ask the question.
Hello, can you hear me?
Hi,
Yep.
I can hear you well. Thank you.
Thanks for the nice talk. My question is, I don't know if this was done, but like, so you are basically producing a selection function, kind of, also for the observation of massive black hole binaries, in the sense that if I observe a binary, then it's more likely that it's coming from, say, a galaxy that is not spherical. So can we actually use this selection function? Do you think we can use this selection function also when doing EM follow-up? Like, say that we have a lot of possible sources and we can exclude some of them based on this, right?
I love your question. Let's just, sorry, I rushed through so much and it's a very early morning for me, but let me just take a step back and say that, remember, binary black holes themselves in galaxies haven't been discovered yet. So when we say, you're absolutely right, because there's a selection effect, but the selection effect is that we look for galaxies that have well-measured properties with a central black hole. And then we drop a black hole in a simulation that has a certain mass ratio or a certain distance. So that second black hole, not observed. However, your intuition is right. I think what we can do is say, well, if this system is very spherical, or it looks like it has a core at the center, or it's not rotating, we can say that that galaxy is more likely to have, if there's a merger in that of black holes in that system, that merger would take a long time. Hopefully that made sense. Did that help a little bit?
Yeah, thank you.
Perfect, thank you.
Okay, any other question? So I have one. So this relation, yeah, it's indeed interesting. So my question is this, prediction based on some physics or totally empirical?
This is empirical. There's some things that help me to recognize that it probably is based, it has a physical basis. And this helped me because I'm always worried about the simulations having a numerical problem. But this is kind of a well-known relation, saying that the hardening rate is very related to the stellar density in the velocity dispersion too. We didn't have that in this model, but actually it's tucked into V over sigma. So the fact that this is so tightly correlated made me think that even though it's empirical, it likely has it likely has some physical basis and is not just numerics.
Okay, so you were saying that the qualitatively consistent. Okay.
Yes.
Sounds good. All right. Any other questions? If not, let's thank the speaker again.
Thank you.
Thank you, Kelly, for the exciting relation. All right, so let's move on to the last one. So the next speaker is Nathan Stanley from University of Birmingham. He's going to talk about the Bardeen-Peterson effect and its consequences for LISA observations of supermassive black hole binary spin orientations. So Nathan, would you be able to proceed?
All right, thank you very much. One second. Can you hear me and see my slides okay?
Yep, both are good.
Perfect. All right, thank you very much for the introduction. My name is Nathan Stanley. I'm a postdoc at the University of Birmingham in the UK. I'm going to talk with you today about black hole spin alignment and disk breaking and the implications for observations of supermassive binary black hole mergers by LISA. I'd like to give a special thanks to Alberto Sassana and Massimo Dodi for very insightful discussions that we had in Milan. I'm doing this work in collaboration with Davide Grossa, who's also in Milan. So generally, supermassive binary black holes, so if you see BBH on my screen, just think binary black hole, please. These binaries are generally expected to evolve in either gas-rich or gas-rich or gas-poor hosts, kind of in a general sense. And the big hope is that the measurements by LISA of the spin orientations will be able to discriminate between these two formation channels. And so these black holes will have a spin magnitude S or dimensionless spin magnitude chi, but we're going to focus in this study on the spin orientations or the spin orbit misalignments, theta 1 and theta 2 of the more massive and less massive black holes respectively. And as Kelly just explained in great detail, there's many processes that are relevant for producing pairs and ultimately bounded pairs of binary of supermassive black holes. And so there's the processes generally are thought of as depending on as being one or other dominant form of angular momentum loss through the evolution of the binary. And larger separations, the pairing of the two black holes is dominated by dynamical friction against the background stars. And then, as Kelly just explained, the loss cone scattering of individual stars by the binary becomes relevant. And then even smaller separations, viscous drag from disk migration can dominate the angular momentum loss if the binary evolves in a gas-rich galactic host environment. And then the baton is finally handed off to the gravitational wave emission phase at the smallest separations, in which drives the binary to merger. So if we start from the assumption, which is a rather generic assumption, that the binary black holes form with isotropically oriented spin directions, which is to say that there's no alignment mechanisms during the dynamical friction phase at the earliest phases of binary pairing, of black hole pairing, then these isotropic spins, if the binary evolves in a gas poor host, then they will remain roughly isotropic and all the way through the gravitational wave emission phase, which implies that the spin precession experienced by these black hole binaries would be generic, meaning that the orbital angular momentum will precess and nutate about the total angular momentum. And so that's kind of more or less, kind of simpler than the other case, in which the binary evolves in a gas-rich host, in which case the Bardeen-Peterson effect can align the spins during the disk migration phase, but the amount of alignment is very uncertain, and this is going to be the main subject of this study. in which we examined circumbinary disk migration of these binary black holes using a systematic approach to the Bardian-Pedersen effect that was previously published by Davida in 2020 and others in 2020, which the Bardian-Pedersen effect basically is a combination of lens-Turing precession and viscous interactions with the disk. And the setup for this binary, basically, this is a larger circumbinary disk, which is kind of the leftovers of the gas from the galactic merger. And the binary black hole carves a cavity in that circumbinary disk. And little mini disks or secondary disks form around each black hole. And those are the accretion disks. Those are the disks that the black holes are actually accreting from, those little secondary disks. And that's where the Bardian-Pedersen effect is relevant, in which basically what it does is that the inner region of the disk aligns on a shorter time scale to the equatorial plane of the black hole than the outer region of the disk, which is at, kind of at the same time working to align the black hole spin with the larger circumbinary disk. And so it's a very dynamical and complicated thing. And over the last decade or so, hydrodynamical simulations of the Bardian-Pedersen effect have shown that if the inclination of the disk is sufficiently large, then the disk can actually break. And recent studies by Rebecca Nealon and others have confirmed that this disk breaking is a physical result of the hydrosims. And perhaps it's worth saying that the model that I'm using from Gross et al. 2020 to model the Bardian-Pedersen effect is a semi-analytical model, which actually does capture this critical angle phenomenon where the disk breaks, in the sense that the evolutionary equations of the disk actually break down and there's no physical solutions. And further subsequent studies show that in the region of the parameter space where these semi-analytic models break down is actually basically exactly where the hydrosim studies show that the disk breaks. And so we can confidently move on and use this model and assume that in the regions of no physical solutions, that's where the disk actually breaks. And so for simplicity, because nobody really knows what happens after the disk breaks and it becomes very, very complicated, for simplicity, in our model, we just are going to assume that when the accreting black hole, encounters a critical disk angle, we just assume that the alignment ceases and we hold the spin orientation constant for the remainder of the gas-driven in spiral. And so if we look at a simple output of these model assumptions, we have the full in-spiral, we have the in-spiral evolution of the binary black hole spin orientations of the more massive black hole on the left and less massive black hole on the right, through the disk-driven in-spiral phase and the gravitational wave emission driven in-spiral phase. Starting on the very left, look at the left panel, for instance. Binaries with, so this is the distribution of binary black holes with isotropically oriented spins initially. And so binaries with initial spin orientations that are sufficiently below the orbital plane will experience some alignment and then encounter a critical angle, after which we hold the angle constant until the decoupling separation, which is where this kind of sharp transition to the gravitational wave emission phase begins. And in reality, it's not going to be such a sharp transition. It's going to be more smooth, but we're just trying to encapsulate the essential ingredients here. If the spin orientations of the black holes are sufficiently near the orbital plane initially, then basically the disk shouldn't exist. It is the black hole spin is initialized at an orientation where the disk shouldn't exist, and so the spin orientation doesn't evolve at all during the disk migration until the gravitational waves take over. But if it's initialized with orientation sufficiently above the orbital plane, then the alignment, depending on the other parameters of the disk and the black holes, can align quite efficiently and remain aligned all the way to merger. So there's lots of free parameters in this model, as you can probably imagine, and I don't want to get into the weeds of it. And so it's actually helpful that we can kind of boil down the essential dynamics into two main parameters. And so kappa governs the effect of the companion on the accretion of each black hole, where kappa sub I is the initial kappa, so the value of kappa at the initial separation, which determines if the spin begins, basically, if it begins at a critical angle. So the initial kappa tells you how likely are you to not experience any disk, any alignment at all from the Bardian-Pedersen effect. The other parameter, omega, governs the relative contributions of the in-spiral and the alignment. And so basically a large omega implies that the alignment is happening faster than the in-spiral. And so more generally, though, omega and kappa depend on both masses and spin, on the masses and spins. And so we have two of each for a given binary. And generally, the omega 1 for the primary black hole will not be equal to omega 2 of the secondary black hole. Same thing with kappa 1 and kappa 2. And only in the limit of equal masses will we have the equality of the omega 1 and omega 2 and kappa 1 and kappa 2. Or approximately. And so what we can do is reduce the full parameter space to just 5 essential parameters. We have the two, omega 1 and kappa 1 for the primary black hole, omega 2 and kappa 2 for the secondary black hole, and then the dimensionless viscosity parameter alpha, which is the good old-fashioned Suneyev-Shakura viscosity parameter. And then if we can understand how the spin orientations evolve according to these 5 parameters, then we can relate those to the more physical and measurable parameters, more easily measurable parameters, such as the black hole masses and spins. Here's a figure of some contour lines as functions of the total mass of the binary and the mass ratio of the binaries. And instead of looking at the individual omegas, we found that it is more helpful to look at their sum, which are the blue lines, and the ratio of the omegas, which are the green dashed lines. And kind of intuitively, if you take the ratio of the omegas, it is basically independent of the total mass, but depends strongly on the mass ratio. That's why those green dashed lines are vertical. And the sum of the omegas is rather non-trivial, but it's more sensitive to the total mass of the black holes. That's why those blue solid lines are horizontal. And then the orange dotted lines and the red dash dot lines are the initial kappas for the two black holes, which we see for larger total mass. As you look upwards in this plot, the initial kappas and the sum of the omegas, the blue line, generally increase, which implies that more binaries will reach a critical angle and align more quickly for larger total mass. And if we go to the right of this plot, as the mass ratio goes to unity, the initial kappas become equal. The ratio of omegas also approaches unity, which implies that both black holes will align quickly if the sum of the omegas is large. And so you can imagine there are regions in this parameter space that are more favorable than others to produce highly aligned binary black hole systems. And to try to get a feel for the general behavior of this of the spin orientations, for simplicity, let's assume that let's assume that the two initial kappas are equal. So there's only one initial kappa for now. And let's assume that both of the omegas are equal to 1, which corresponds to a moderate amount of alignment. And in the columns, and so in this mega panel plot, the columns correspond to different values of the initial kappa. So how likely are you to experience, to begin at the critical configuration? And the rows were varying the viscosity alpha. And you see in each of these panels, there's a little black box or a large black box. And this black box contains the binaries that have a black hole which is initialized at a critical angle. And so in this plane of the two spin orientations, the binaries are evolving from the blue crosses to the red circles, but the ones that are contained in this black box don't evolve at all because they started with the disk that was already broken. And we're assuming that the angle doesn't evolve at all. And the size or the area of this black box in this plane is proportional to the value of the initial kappa and depends on the value of alpha non-trivially. And generally, if you see in the top row for lower values of alpha, the black box is larger, is relatively large for any value of the initial kappa. And this implies that binary black holes that evolve in low viscosity gas-rich hosts will be difficult to distinguish from those that evolve in gas-poor hosts due to the occurrence of this critical angle phenomenon early on in the binary, early on in the disk migration phase. But as you increase alpha, generally the black box can get smaller, unless you're starting at a very high initial kappa, which is to say you're starting the disk migration phase at a very small separation, and so the effect of the companion is very large, which can induce this critical angle thing. And that's why these left column plots are basically, the black box is so large and there's no evolution there. Next, let's look at the dependence on the omegas, and let's fix the viscosity.
You have one minute left. Sorry, I forgot to tell you. Yeah, 1 minute left.
Can I bleed into my question time a little bit? Is that okay?
Sure.
Thank you. I have a problem of having too many results. And so if we fix the viscosity and instead vary the omegas, as you increase the sum of the omegas, the alignment is more efficient. And so that's why more binaries evolve in the bottom two rows and in the top row where the sum of the omegas is small. And if the ratio of the omegas, which is varied in the columns of these panels, if the ratio is less than 1, then that means the secondary is aligning more quickly. And so these binaries kind of stack up on horizontal lines in this plane, like in this panel in the middle left. Or if it's greater than 1, then the primary aligns more efficiently and they stack up in vertical lines in this plane. Now, putting those things together real quickly, returning to the contour plot, Lisa will likely observe binaries with total mass, I mean, roughly, kind of naively, between 10 to the 5 and 10 to the 8 solar masses. And from what we just learned, if the total mass is sufficiently large, then binaries can experience sufficient alignment because some of the omegas will be large. But however, if the total mass is not too large, then few binaries will encounter the critical angle. So this implies that there's kind of like a box in this parameter space that contains binaries that are most likely to be highly aligned and to be observable by Lisa. And I have a little movie here. So more generally, if you choose the total mass, the mass ratio, the spin magnitude, and the viscosity, you can hopefully see how these, here we go, how these binaries actually move in the plane. And so in this case, the secondary is aligning more quickly than the primary. That's why they go up faster than they go to the right. And then they settle down into these kind of well-localized regions of the parameter space. You can kind of cut into 4s, depending on where they actually started. And so binaries that start in the upper right quadrant will end up having both spins aligned. Those that start in the bottom right quadrant will only really have their primary aligned. Those in the top left will have their secondary aligned. And those that start in the bottom left portion of this region, of this plane, will have both spins that encounter the critical angle, and they kind of pile up near the edge of this black box, which implies that they will maintain misaligned spins until the gravitational wave emission phase, meaning that they will also exhibit generic precession as if they had actually evolved in a gas-poor host. And I'm going to skip this and move on to my last slide real quick, which everything I just showed was basically about disk migration phase. But if you take a subset of those binaries that we just looked at and look at how they evolve in the gravitational wave-driven phase, they will essentially evolve on lines of constant chi-effective, where chi-effective is this post-Newtonian conserved quantity that depends on the masses and spins. But the mass ratio and the spin magnitudes are constant in the post-Newtonian inspiral. And so that's why these things evolve on lines of constant chi-effective in this plane defined by the spin orientations. And the green triangles, so that's shown by these green lines, and the green triangles show the actual spin orientations at 10m, which basically the effect of the gravitational wave emission serves to kind of blur those those subpopulations that we just talked about. And so this work will be published very soon, so please keep an eye out for it. And to summarize very quickly, if we assume rather generically that binaries are beginning disk migration with isotropic spin directions, then there exist degeneracies between the spins of binary black holes and gas-poor hosts and gas-rich hosts with low viscosity, very high total mass due to the disk breaking, and very low total mass due to the inefficient alignment of the Bardian-Pedersen effect. But otherwise, it can align the spins and create subpopulations defined by whether one or both or neither of the spins are aligned. And these subpopulations will exhibit different spin precession in the LISA band, which will be the focus of a follow-up study. And last but not least, if LISA measures binary black holes with predominantly aligned spins, then this implies that formation in that they formed in a high viscosity gas-rich host. That's all I have for you. Thank you so much for listening.
All right, thank you so much, Nathan, for the wonderful talk. Yes, indeed, it was so many results that you had to show. Very good. So any questions from the audience? I guess we can take one or two. I think I have one quick one. So you showed this QM, plot. Sorry, I disabled my video. Anyway, so you showed this QM plot, yes, and then you had this, multiple lines, and I wasn't able to, understand, these multiple lines, the meaning of these multiple lines. Can you quickly explain that again to me?
Yeah, I apologize. It's a lot, I know. These parameters omega and kappa are very nice because they depend on all the other free parameters of the system. And so we can kind of use omega and kappa as like proxies for how the spin orientations will evolve as a function of the more physical parameters like the total mass and the mass ratio and the spin magnitudes. And so basically the first look at the initial kappas, I think they're simpler, which basically says how likely are you to not have your spins evolve at all because the disk starts off being broken. So the higher the kappa, the more likely it is that you experience this disk breaking. And so these are the red and orange lines here, which are strongly dependent, the magnitude of the kappas are most dependent on the total mass, on the magnitude of the total mass. And so for larger total mass, larger initial kappas, the red and orange lines go upwards, and you're more likely to begin the evolution with a broken disk, which is to say you're not going to evolve the spin orientation at all. And then
okay.
Right.
I think I got the essence of this plot. Sorry. Yeah.
And then because there's two things: how likely are you to have your disk break, and then how fast is the alignment, and they kind of compete, right? Maybe you begin with a broken disk, and so you can't align at all. But maybe you don't begin at a broken disk, but the alignment isn't efficient at all. And so that's what the blue line shows: how efficient is the alignment, the sum of the omegas. And so a larger omegas mean more efficient alignment. And so there's this box I can draw here to where, you're not too massive, like up here, to where your disk is just always broken, and you're not, too light, like down here, to where the alignment is not efficient enough. And so there's kind of this like Goldilocks region here to where, you don't start out at a broken disk, and the alignment is efficient enough to actually, for LISA to potentially observe the aligned spins.
I see. Yeah. Okay.
Yes. I'm sorry for that. And there was a lot there. I'm sorry about that.
No. It's all right. I guess. Well, yeah. I see the chat window. Alice there saying, "Would you like to show the slide you skipped over? If we don't have another question." Yeah, we don't.
Sure, I'd love to.
Yeah, since this is the last talk. Yeah.
Sure. And so kind of so the question, the kind of like, I guess from here in this orange box contains the binaries that encounter a disk breaking in the course of their evolution through disk migration phase. And if we want to know how large, if you count how many binaries did this from the whole distribution, in this case, it was about 35% of the binaries will encounter this disk breaking of both black hole disks. And so instead of, if you hold the masses and spins constant and vary the viscosity alpha, and you count those fractions, the ones that have both spins encounter the disk breaking, which is the blue region, it's where both spins encounter the critical angle and thus remain misaligned, significantly misaligned. And then the three other regions are the fractions of binaries that only have one spin that gets aligned. Like the primary, I think, is the orange. The green is only the secondary gets aligned. Then the red is where both spins get aligned. And so they sit up in that top right corner of the spin plane. And kind of intuitively, just to finish it off, intuitively for low alpha, which alpha is one of these kind of controversial parameters, but if you take it with a grain of salt, for low alpha, that means you have low viscosity disks, and so they're more prone to breaking. And so the fraction of binaries that will encounter the disk breaking kind of explodes. That's why the blue region gets larger. But as you increase alpha, the disks become more viscous and less prone to breaking. And in this case, for the masses and spins considered here, these fractions basically converge to a quarter each, about, because that black box in that spin orientation plane goes to basically a point. Because fewer and fewer binaries are likely to begin at a critical configuration for very large alpha. Thank you for that.
All right. Thank you so much, Nathan. And I think this concludes, well, thank you for the talk, Nathan. And this concludes the parallel session, multi-messenger astrophysics and supermassive black holes for the day. Thank you so much for joining us and watching us, and see you next time. This is the end. Bye-bye.